Oh, good. So all this nonsense can be on the recording. Good, good. Well done, me. Hi, friends. Week 2. Here we are. How you doing? Yeah, that looks like something. It's like a head nod in the affirmative. I have this Indian friend, and I can never tell which way she's nodding. She's got this like kind of like figure 8 nod. I make fun of her about it all the time. But I think it's like a cultural thing for sure. Never know if she's saying yes or no. And sometimes she's saying the word no, but she means yes. She's saying no, but she means yes. So I love her. Any questions on anything? I know there's a few questions. All right. Let's take a look at something. So we have a quiz on Friday, right? Little quiz. Are you okay, Sophia? Okay. You just didn't want to hear there was a quiz on Friday. Yeah, fair enough. Who can blame you? But it's just, I'm literally going to pick one of the web work problems, and then what else is on the quiz? Sine and cosine graphs. That's it. And guess which one I'm not going to pick? The ones everybody's having trouble with. Okay? But I want to talk about them today, just really quick, because I go through the web work and just look. If you've done something more than like 10 times on web work, ask me about it. Just stop, because I've seen like valiant efforts, like kudos to the folks who are working these things unbelievable amounts of times. But after 10, just hit me up. We'll talk. It might not be you. It might be web work. But the things I'm going to talk about today are definitely not web work. So this is just like quick before we even get into, I want to do some quick trig stuff. This is a quick recall on what we're going to do here. So we've got some problems like this. You're given a triangle, and you've got like one side, and you've got the other side, and they ask you to do something like this. You've got some angle theta here, or x, or whatever it is, and then they say find the sine of theta. This might be a problem some of you have struggled with on the web work. So how do I find this side? Because I sure would like to have all the information. How do we find that side? Yes, Sam? Pythagorean theorem. So I'm going to call that whatever letter I want. It's H for height. Just, what the heck. Sam, what's the Pythagorean theorem? Tell me about that, and that.
So it'll be 3 squared plus H squared.
Yes. Equals 12 squared. And that is the Pythagorean theorem. And man, this Pythagoras, thousands of years ago, did some shit with triangles. And today, we still are calling the name of Pythagoras. This is madness. Can you imagine? I don't think anything I've done or will do will be lasting that long. I mean, I hope not, because it's probably not going to be good stuff. It's going to be some weird thing I did that got posted on the internet. So I solved this for H. And let's see, so I get H squared 144 minus 9, so that is 135. And then H is, God help us, whatever the square root of 135 is. Who knows? Who cares? It's a number. We'll type it into our calculator and have it. Let's just leave it there. Sam's going to give us, he's actually got to do it. It is approximately 11.6. Cool. Thank you. So, one thing with web work, like a little tip, I would leave the answer like this until I come up with my final answer. Because if you did this approximation but didn't do, because I imagine, Sam, there were many decimal places past that. Sometimes web work needs high precision. So just keep everything full precision until the very end and then pull off your decimals. Because this If I use this, it's going to produce an error in my final answer, and WebWork is a little particular. So then I come up here and I remember something great about right triangles and trig functions. If this is the height, hold on. I wish I hadn't said h there for hypotenuse. Let's put hypotenuse here. Hypotenuse, this side next to the angle that's not the hypotenuse is called the adjacent side. And the side opposite the angle is the opposite side. So that's hypotenuse right there. And then I remember this little mnemonic device. You've learned this at some point, SOHCAHTOA. Sine is opposite over hypotenuse. So sine of theta is opposite over hypotenuse. Cosine of theta is adjacent over hypotenuse. And then tangent of theta is opposite over adjacent. So that's the adjacent over hypotenuse. That's the opposite over adjacent. These are good things. You will need these throughout the semester, most certainly. And now from here, I can answer that WebWork problem. And so when I come through and do this, was this the one you were working on, Sophia? Does this kind of? We'll take a look at it. So email me, and I'll take a look at what, because I thought I did. I wasn't sure. So at least you're doing it like this. You got the right path. Right on. All right. So any questions on that? That's like kind of one of them. And then there was this other one that I'm going to talk about, another trig one, the very last problem, which may have been a little stressful for you. It was solving a trig equation. So let's actually, it was something like this. For x, solve tangent of x for, and I'm going to make up a problem here. Square root of 2. So now, there's a lot more to talk about here. First off, when I'm asked to solve a trig equation, I want to kind of see if it's related to one of these special triangles. So this is called a trig equation. And we have these special triangles that you should definitely have by your side. There is the 30-60 right triangle, and there is the 45-degree right triangle. And of course, this little, if you're unfamiliar with that, that's a right angle right there, so 90 degrees. The sides on these are going to keep the same proportions no matter how big or small this triangle is. So the way I remember this is the shortest side is opposite the smallest angle. The hypotenuse is the longest side. And then if I couldn't remember what this was, I could do some Pythagorean theorem stuff, or I could just have this picture ready, and then I'm ready with it. So this is a 30-60 triangle, and you can do any work with these as needed. But when we do calculus, unless we're actually doing a physical application, we're going to use radians. So this is pi over 6, pi over 3, and here's those relationships in radian mode. Same thing for this dude. Let's see. So these two angles are the same size, so their opposite sides are the same length. And then I could use good old Pythagoras to get that if I needed. And I also want the radian version. Pi over 4, pi over 4, root 2, 1, 1. So now I can answer some easy questions. Like if I said to you, what is the cosine of pi over 4? And then you go, oh wait, cosine is adjacent over hypotenuse. And I come to this picture and I say, yes, I can pick either one of these. It's the adjacent side 1 over the square root of 2. And I can knock that out. So you can pull lots of special angles out of this information. This and SOHCAHTOA, gonna rock a lot. So now let's look at this picture here. I know that tangent is opposite over adjacent. So, yeah, none of these are going. Oh, shit. This isn't the one I want. Sorry. Can we change this to square root of 3? Sorry. You would only get one. Like the ones on WebWork, the problem that we're thinking of is definitely one of these special triangles that's up there, because there's like a square root of 3 involved in it, if I recall. I think it was negative, but we'll get to that in a minute. So I look and see here which of these triangles could possibly be involved in this. And the only one that's got a square root of 3 is this guy. So I know that triangle is somehow involved in this scenario. And now let's think about how we're going to solve for these things. Notice that this is a positive number. Positive square root of 3. That's important, because what I'm going to do is try to put that triangle in some of these 4 quadrants in a way where the tangent is positive square root of 3 over 1. Notice there's no fraction there. If there's no fraction, make a fraction. So I'm forcing that into a fraction because all this trig stuff is fractions. And if I had that over that, or that over that, I got square root of 3 stuff. So, all right. This is another table you should know. Have you seen this? All students take calculus. This, like, I'm basically teaching you from old man knowledge. This is like back in the day, you know, we ride whatever horses we did into school. Has anybody seen this besides me? Okay, okay, all right. So, if I have an angle and it lands in this quadrant, all the trig functions are positive here. So these letters stand for the trig functions that are positive. So any angle that I have in here, the sine, cosine, or tangent of this angle is going to be positive. If I'm in this quadrant, the only trig function of this angle right here that's going to be positive is sine. But think about why that is. Sine is opposite over hypotenuse. And the opposite side is positive there. So that's where you could kind of tie this information together. So sine is positive. In this quadrant, only tangent is positive. And here, only cosine is positive. So now I come back to my equation. I've got a positive tangent. It's got square root of 3 over 1. I know that's this triangle. I just need to fix this triangle into the quadrants where tangent is positive. So here or here. These are where my angle must live because tangent is positive of x. Right? I'm trying to find this angle x whose tangent is this number. So it's either got to land in this quadrant or in this quadrant here. So I'm using that all students take calculus little mnemonic device. Okay, so tangent is opposite over adjacent. So when I draw this triangle in there, and your hypotenuse is always going to be the thing you draw from the center here. So this will always be the hypotenuse, no matter how you draw it. If you drew in here, it would be the hypotenuse. I need to have the opposite side have square root of 3, and then the adjacent side to have 1. So notice how I fit that triangle in here, and now look, that angle x has a tangent of square root of 3 over 1. So whatever that angle is, and I can figure out what it is from that picture, that's one of my answers. The other answer is over here in this quadrant. Your right angle's always made with the x-axis, so you always have a vertical line. You don't do this. People occasionally do that. You've always got triangles that are made with the horizontal axis. So down here, I've got a tangent that is square root of 3 over 1, but if you think about it, that's because this is negative square root of 3, right? Your y-coordinate is negative, and your x-coordinate is negative. So now the tangent of this angle, this little reference angle, which is the same as this bigger full angle, has a tangent of square root of 3 over 1, opposite over adjacent. So all I got to do is look and see which angle is opposite the square root of 3, and it's this, oh shit, yeah, I did it right. So the opposite the square root of 3 is this pi over 3. So this must be the 60-degree angle, pi over 3. This must be the 60-degree angle, pi over 3. And I'm just drawing that little triangle. I still have to measure from the positive x-axis to get the full angle. So could someone tell us how I move from this little pi over 3 wedge to the full measure of that angle? What do you think, Addie? Sorry to bust on you. You're not sure? That's all good. Is anybody sure? Sam, you're sure? You're willing to take a stab at it? Yes. So if this little wedge right here is pi over 3, how much is this full sweep from the positive x-axis to there? What was that? 4 pi over 3? Is that what you're going to say, Leo? How did Addie get that?
Given the fact that just taking the half circle is 180 degrees.
Yes.
Is pi, and then adding the pi over 3, right, or 60 degrees.
I love it.
You get 4 pi over 3.
That's how you get it. So a half sweep is a pi. What's 1 plus a third? It's 4/3. So this is 4/3 pi, or 4 pi over 3, however you want it. So the solutions to this equation are x equals pi over 3 or x equals 4 pi over 3. And that's how you do the last problem. No, it's not the last problem. It's close to the end, right? It is the, yeah. I know it's one a lot of people suffered on greatly, so I wanted to talk about it. Does this help a bit? Asha, does that help a bit on that one? Okay. Any questions on any of this or any other web work? Like I said, I went through and looked for what people were snagging on, and these two were the big snags, besides an easy snag that wasn't a snag at all. We good? All right. You tell me. You got to tell me. Your job is to tell me what we need to do, and we'll do it. So that web work is due tomorrow, the end of the day, 11:59 p.m. It's looking good. Some folks have been done for a while. That's great. There's a new web work that opens today, I think a little bit before the end of the class. So there is a web work homework 2, I think, that is I don't know which one it is. There's a new web work up. I'm sure you'll find it if you go in there. I forget what I titled it, if it was 1 or 2.
I do have a question.
Yes, sir.
So regarding homework 0,
so this is 1 then. Yes, thank you. Yes.
do we have to take like a screenshot of it being done?
No, I see that. I just go in and check.
Okay.
You don't have to do anything except work them.
Okay, sounds good.
Or let me know if you can't.
Because my question was, do we have to take a screenshot of it and put it into world class?
No, that sounds like a pain in the ass. No. I will put it in there. So but it takes me a little bit.
Okay.
But I've still got time. It's not even due till tomorrow. So I'm cutting myself some slack on that. So I will record your grades. Yeah.
Okay.
Yeah. Just work them. Let me know if you're struggling. We'll all work together to make it happen. Okay? Any other questions? That was a great question. Okay. All righty. Let's move forward. So this WebWork one, it's probably due, I don't know. Shit, I'm just going to say Wednesday or something, but I think that's probably right. It's Wednesday or Thursday of next week, one a week. Not crazy, not totally unexpected. So let's push forward. Today we're going to head toward talking about what are called limits. And this is actually calc. We haven't done calculus yet, but we're about to enter it today. It's going to be all right. When I say, I've just watched people's expressions when I say things. So I'm like, just making sure everybody's okay. It is going to be all right. All right, so limits. Let's get there the slow way. So first off, here is a position function that I want to talk about. 64 minus 16t squared equals the position of a particle at time t. And we're going to assume that t is non-negative. So I'll say t is greater than or equal to 0. Time's moving forward from now. You should always want a picture of things, and you either produce that yourself or you go to Desmos or your graphing calculator and you get a picture. When you get an equation in this class, look at it. You will gain more insight from that than you maybe are aware. This thing looks like this. At time 0, I'm at 64. And at time 2, I'm at 0. Because when t is 2, I got 64 minus 16 times 4. That's 0. And it's a parabola, so it looks something like that. Let me stop. And let me know, if that makes sense, you kind of like, yeah, of course it's a parabola. And of course it opens down. All right. So what I want to consider, and just see if you remember what this is. So let's just test our memory. What is that? And take a minute, write it out. I could tell you, but it'd be more interesting if you'd recalled it or looked it up or... And this x is bigger than 1, in case you're interested. Hey, Kyla, do you have the first steps on this? Like, just what did you do first for it? Beautiful. Thank you. Thank you. And I know there's more work to do, but that's why I was just like checking on that first step. Okay, so it's s at the end point minus s at the start over the change in time, x minus 1. And then from here, we can do some work, right? We can... And then we have to figure out what that is at 1, which is, I think, 48. Let me know if that's wrong. Over x minus 1. And then 64 minus 48 is 16. And this work doesn't have to be done, but it's probably something you should be in the habit of whittling down and make sure that you can do it. And let me stop and make sure. Does it look okay? Like, looks okay. Any questions I can answer about it? Yes, Asha. Okay, cool. Good question. So S at 1, I plugged 1 in for t here, and I got 64 minus 16 times 1 squared. And so that was 64 minus 16, which I think is 48. But I might, yeah, that's how I got it. Does that make sense? Cool. Other questions? Okay. So we got a nice compact little formula. Let's think about what this picture represents. So 1 is right in the middle here because that's 2. So 1 is right there. And what I've done is I've got S at 1 right here. So that's that. And I've got a point that I told you was a little bit to the right. So that's X. And then that's S of X right there. And what we've done is we've found the slope of this line right here. And that's just not good. Here's a better pen. We found the slope of this line right here between those 2 points. It's close to that curve, but that curve bounces out a little bit. It's round. This is a straight line. So this thing here is the slope. Let's write this out because it's something we want to have always in our mind. This is the slope of the, and I said this word last time, but I'm going to make it formal, the secant line. A secant line is just a line between 2 points on a curve. Any curve. You got some weird-ass curve, you got 2 points on it, there's a secant line. So the secant line between 2 points, which are 1 comma S of 1, I know that's hard to see, sorry, and X comma S of X. But it's slope. It's a slope, and that's the thing I really want to emphasize. So now we can think about this thing a little bit differently. What if I asked you to find this? We got that formula. What happens when X is 1, i.e. let X equal 1? What happens to this formula? Dividing by 0, yeah. And what do I have on top as well when S is 1? I got a 0 over 0. So notice that when X is 1, and you would probably say, well, I shouldn't let X be 1 anyway, because like Sophia said, I've got division by 0. So here, this is 0 over 0. And that is something you're going to be looking for the rest of the semester. This 0 over 0 is a key that maybe more work can be done. More work can get us an answer. And I'm going to show you the tricks today to doing that. Get us a real answer. And let me motivate that why I even think there's a real answer. So let's sneak up on this. So we're going to sneak up on this average velocity on 1 to 1. We're going to sneak up on it. And we're going to sneak up on it by taking this X closer and closer to 1. And see what happens to our output. What is the value doing? So in other words, first thing I want to crank out is AV of 1 comma 1.1. And then I want AV of 1 comma 1.01. And then I'm going to get crazy and I'm going to say, what is the average velocity of 1.000, 4 zeros and a 1? Holy shit. Well, now you all do stuff because I don't know what the answers are. I need your help. Please tell me. Somebody start at the bottom so we have that one early. Somebody start in the middle. Somebody start up top. Decide where you're going to start. Give me one of them answers. And your phone can be used. Yes, indeed. Do you have a nice calculator on there? Are you using the Apple calculator?
I have this kind of calculator.
Yeah, I got not great feelings in my belly about that one, but You don't? Oh,
I mean, do you want me
is
to
it
use
is it not an iPhone? Yes, I do. But let's put it in scientific mode. Do you know how to do that? Click down here. Isn't that beautiful? It's much better than that blasphemous other thing. If you're not sure how to put your phone calculator into scientific mode, happy to help you. It's not something a lot of folks do. I use my phone calculator all the time. Yeah, you got it. Oh, you got a very fancy one. Anybody got any of these for me yet? You got one? Which one you got?
the middle one.
Middle one and -30. Yep. I actually did work them out ahead of time. I'm just lying because I wanted to see what they did. So I did have that one. I think I didn't work this one, but you're definitely right on that one. And shit, let's get some units in here. Position. Oh, let's just do some meters. So I can slap on some sort of units here, meters per second. For the scientist among us, that's probably more important. Zeus, you got any of these for me yet? Oh, Zeus. Jasmine, you got any of these? Okay, all right, it's all good. Oh, you're doing it. You're getting in there. All right, I like that. You're just writing everything out before you crank it. Eddie, you got any ones we don't have yet? Okay, all right, that's cool. This is the soothing part of math class, where we just relax and do simple computations. What you got, Sam? Oh, nice. Yeah, that looks good. Wow, that's cool. And that's 3 zeros in there? Okay. I feel like this one's like -33 or something. 33.2? 6. Yeah, the 6 makes more sense because there's this pattern of this 1 6 and it got shifted over to be added to 32.
Bottom one is 3.2.
Thank you. Wait.
Yeah.
3.2? I don't think that should be. I would check. It should be 32 point.
You're right. I have front of 0.
Okay, cool. Okay, good. Okay, thank God. Thank God. I didn't work it out, but I had a sense of what it should be. Do we see anything happening here? Are we stabilizing as we get closer to 1? We are stabilizing. Notice that here you're like, oh, from here to here, I don't know. But from here to here, I'm going to be bold, and somebody's going to test me on this. I'm going to say that if I have 1.1, 2, 3, 4, 5, 6, 7, 1. I mean, like that's not even humanly observable. This difference here, we couldn't see it on the board, but I'm going to wage. That is 1, 2, 3, 4, 5, 6, 1, 6. Could somebody just check me out? It is, yes! Aha! Oh, yeah, and here's the evidence. Beautiful. So there's a pattern happening here. We could even say that as x approaches 1, so this is some language that we're going to get in and make a little more formal here. As x approaches 1, and this is technical language, this isn't just goofiness. As x approaches 1, comma, the average velocity from 1 to x approaches, what do you think? Negative 32. Do you see how we're getting closer and closer to that? Is that negative 32 relevant? Does somebody know any physics in here? What's negative 32? Where's that coming from? Physical constants. Gravity. That is the acceleration of gravity. Interesting. This is negative 32, and we have meters per second, but I do just want to note that negative 32 equals the, and that is, what is that? Feet per second squared. That is the acceleration of gravity, g. So this problem was kind of actually based on a real physics setup and worked backwards. That's why we're seeing that number showing up. So, interesting that this is what we get when we try to compute it directly, but when we sneak up on it, 0 over 0 actually turned out to be negative 32 here in this case. Isn't that weird? That's calculus. So first off, here's one thing I want you to remember from today. This means you do more. And I'm going to show you what I mean by the more here in just a minute. There is more to do. And let's actually start with this mofo right here. I shouldn't call it a mofo. It's a good friend, but I would call my good friends that. Not in a professional setting. So let's take a look at this again. So we've got AV of 1 comma x, and it turned into 16 minus 16x squared over x minus 1. If we let x equal 0, or excuse me, x equal 1, we get 0 over 0. Oops. The first thing that probably means is that you need to factor. So when you get 0 over 0 in any expression, factor, cancel, and redo. Those are Dr. T's, that's my algorithm for doing what we're about to do today. When you see 0 over 0 in this class, there's something for you to do. In most cases, there's a few special things that we'll remember. But when you can factor, do it. So, hey, could you take a minute and factor that thing? That sounds fun. I got all sorts of stuff for you to do today. Hopefully we're still recording. Yeah, look at that. You should see something cancel. Please bring that from now on. Do you have a pen? Okay. Otherwise, it's just boring, right? You gotta at least move your hands and shit. Can you do it in your head? I figured so. But humor. It's okay. Just humor. No, it's not. If you can do it in your head, I just like the doing is like soothing also. Yeah. You agree? Okay, good. We want you soothed. Not trying to be a control freak. Yeah, looking good. Looking great. Yeah, beautiful. Beautiful. And then you'll see something that'll cancel there. Yep. There's a couple of terms that cancel out. Doing okay? Yeah. Oh, beautiful. Yeah. And once you see that cancellation, I didn't check Josh here. I'll check, but I bet. Oh, yeah, that's right. I already did. That's right. Looks good. Once you see that cancellation, you see that things become a little easier. For me, I first pulled out the 16 from the top and bottom. You don't necessarily have to do that, but it feels like a kind of natural thing to do. And then from here, this is the difference of two squares. If I have something squared minus something else squared, and I like to use these symbols because then you can do really complicated things that aren't necessarily trivial. And then they maybe, might have sines and cosines and all sorts of weird shit in it. So this is what I'm going to use up here. I've got 16 times 1 squared minus x squared. So that is 1 minus x times 1 plus x. And then the bottom is still x minus 1. Looking good? Okay, cool. And these two look ridiculously similar. So how do we tweak them? This is the opposite of this. So I'm going to pull a negative out of that one and make it x minus 1. So the x becomes negative, the x becomes positive, the 1 becomes negative. And then I flip their order. So in other words, the opposite of that. So if I multiply the negative times that, or pull a negative out, it's this, which I rewrote as this. And then that's times 1 plus x over x minus 1. Cancel. Negative 16 times x plus 1. So computing, yes, Leo. Thank you. Yep, thank you. Good call. Yeah, keep me honest. Questions on that? We good? Cool. So now I've got a sweet formula, and I can let x equal 1 here. So notice here that if I let x equal 1, I don't have division anymore. And what I actually get is negative 16 times 2, negative 32, the thing we sussed out with this. So the rule, the lesson here is that when you've got 0 over 0, and I'm asking you to do something that gets an answer out of this, factor, cancel, try it again. So let's actually get some official notation in here. This problem that we just did, if I were to ask you this, here's how I would ask you to do it. I would say find the limit. We'll talk more about what that word means in just a second. But this problem was find limit as x approaches 1 of, and let's just grab the formula, 16 times 1 minus x squared over x minus 1. Find that. So that's fancy. So this is the limit of this expression, and I'm just showing you how to read it, as x approaches 1. This is super important here. This isn't about what happens at 1, even though that's how we found it. It's what happens near 1. So what this question is asking is, what does the output of this expression approach just like this other one approached negative 32 for its output, as the input x approaches 1. And approach means get close to. Get close to. And the way we can solve this, so step 1, to find, here's your algorithm, to find limit as x approaches c of some expression. What does this output do as I approach an input of c? Step 1 is try to plug x equals c into f of x. So i.e., find f of c. Just literally plug it in. Plug. 2, if the answer is not 0 over 0 or non-zero over 0, so if you don't get that or you don't get that, you're done. The answer is the plug and chug from step 1. And you're super happy. Let me show you what I mean. Let me show you what kind of joy you'll find occasionally. So for example, let's go back to our buddy there. Find the limit as x approaches 2 of 16 minus 16x squared over x minus 1. I'm going to plug 2 in. I'm just going to plug freaking 2 into the top and 2 into the bottom. So I'm going to check with the plug step, and I've got 16 minus 16 times 2 squared over 2 minus 1. Hey, there's no 0 in the bottom. Yes, it's the 0 in the bottom that makes things start to get scary. There's no 0 in the bottom. I got a 1, and on top I got a 0. That's okay. What is that? 0. Good old 0. That's our answer. Plug it, get your answer, move on. Let's do one more. Can you please find this limit? Limit as x approaches 2 of x minus 2 over x squared plus 3x minus 10. Let's find that limit together. I can start bringing in some more challenging things for you to do too, if you would like.
I would like that.
Okay.
Yeah, I've taken calc, like A, B, C. I've taken calc classes. I just don't have the credit for it.
Oh gosh, gotcha. Cool. Okay, awesome. That's great. So we'll find some more evil things for you to work on, and trust me, I will. Just a heads up, you should get 0 over 0 when you plug. Okay, good. That was the plan. Sometimes my plans made previous days don't always pan out. Did you get one? Maybe. Oh, maybe. Yeah. Really? I don't know about that. I don't think that one's possible. Are we talking about this one here? Yeah, okay. Let me see what you did. You got that, yeah. There's a 1 left on top. When you factor that out, you don't get a 0 on top.
Oh, you're right.
There we go. That's how you got it. Okay, it's all good. You got the right plan. You just made a weird brain barf. Yes.
I have a question.
Yes, sir.
How do you get a 0?
Oh, good question. I don't get 0, do I? On that top one. Did anybody else not get 0 on the top one? I don't know why I thought that was 0. Isn't that ain't 0, is it? What is it actually? Negative. Yeah, because this is negative 64, right? Or this is 64 right here. 16 minus 64 is negative 48. So actually, sorry, I got a little excited. I was like reading that 64 in there and like in my brain, not, yeah. So great question. Thank you. Joshua rescued us from my troubles. And once again, that looks good. That looks good. So you put in the 2. So now what did you get in the bottom? What's 4 plus 6 minus 10? 0. Aha. So we got a 0 in the bottom too. Yeah. So now you got to factor that guy. And you can. And then cancel and then try it again. Does that make sense? Okay, cool. If you factor that bottom, you might need some factoring practice. But I believe it factors like this. My FOIL, when I do FOIL, first, outer, inner, last, the O and the I get me 3x. Everything else checks out. And of course, I did get a 0 over 0 when I did the plug. And I built this to have a 0 over 0 in it, so I know that. And then you cancel here, and that's going to actually cancel out your trouble. It removes the zeros. We get 1 over x plus 5. And now I plug in and get a lovely 1/7. Cool. Yay. I saw a number of people getting 1/7. Is there any questions on that? We're good. Okay. So there's some of this stuff on the web work, right? But then there's something else, and this is all picture-based. So I want to talk about this. I want to talk about when limits don't exist and the ways that can show up. So let's talk about piecewise functions, piecewise defined functions. So if I have a function, f of x, and I got to get my notes out because I created a pretty one. It's written like this. This is a brace. This is like a giant brace. So it's kind of like a long S and then the mirror image of it. Spits out a 1 minus x if x is less than 0. So there's an unspoken if here that you might see a comma or a semicolon, but this is the output formula if the input is in this range. So this is the input range for that formula. And we'll get to it in a second, just in case that's not quite clear. It's going to spit out an x squared if x is 0 up to 1, but not including 1. And then it's going to spit out x if x is bigger than or equal to 1. This is a key thing for limits and calc in general. Can you see that okay, Zeus? Yeah, cool. You're good, Jasmine. Okay, cool. Everybody good on the function? We can all see that okay? Awesome. Let's make a picture. And this will help us understand what this thing means. So first off, if I just said y equals 1 minus x, what is that graph? What you think?
Like the y-intercept one.
I like it.
It's
Yeah.
like this way.
Yeah, it's like a line sloped downward. Yeah, it's a line with slope what?
Oh, -1.
-1. Beautiful. Yeah. So it's a line with slope, and probably Sophia was converting in her head maybe to something like this, your slope intercept form, where this thing is actually -x plus 1. So the slope is the number in front of the x, that's -1, and this is your y-intercept, which you got right off the bat. Or you just plug some points, right? But hopefully you realize it's a line and it's straight. That's really important. So when x equals 1, this thing would be here. But so I'm going to actually sketch out the whole thing for a second. Don't get too crazy with that if you're using pens, because I'm about to erase some of that. This is the formula, but only when x is negative. So I can't use any of this stuff for that formula. So I'm going to erase it, because that's not the formula I use when x is bigger than or equal to 0. That's a different formula. And in fact, I can't actually even get to x equals 0, so I put an open circle. So you might want to put a little note here. Since x is less than 0 on this part, we open circle the end, the x equals 0 value. Does that sound good? You seen this before? Yeah, might be a while. And then what's this graph? So now I've got y equals x squared. What's that? Parabola, right? Good, the classic parabola. Kind of comes like this and up this. Except this parabola, I'm only going to grab this chunk here. So you see how I've kind of divided the input space into 3 strips. Over here we've got x less than 0. Here we've got 0 less than x less than 1. So in this region, I can actually use x equals 0. So when x equals 0, output is 0. And I can get there because I've got equality. But when x equals 1, I would spit out a 1 squared, but I can't quite get there. I'm going to stop. And you're going to hopefully let me know if I need to explain any of that. Because we're almost done. Now we're going to use this piece. And this piece says that when x is bigger than or equal to 1, I just spit out the x value. So that's just y equals x in this region. And that means when x equals 1, I can get that. I filled in that circle, and I just have this diagonal line that looks like that. So I got a really weird graph. Quite odd. And now I can ask questions about that. But I want to talk about a few things before I ask questions, because I got actually a different one. Okay, so first off, let's talk about left and right-handed limits. So this is a kind of a subtlety of what we just talked about with the limits. If I write limit as x approaches a point C, and I put a minus sign here, the way I read this is x approaches C from the left. And what that means is values less than C, i.e. x is always less than C. I can get as close to C as I want, but I have to be on the left-hand side. And now here, so put f of x. And if I write lim as x approaches C positive of f of x, that means I'm approaching from the right. So how do you keep this straight? Negative numbers are on the left, positive numbers are on the right. And you're approaching either from this way the positive, or this way, the negative. So this is x approaches c from the right. And what that means is that I only consider x values that are bigger than c. I might have c plus a billionth, so I'm just a hair's width away from c, but I'm on the right side. And you can see how that changes things over here. Look at when x equals 0. On the left side, you got that line. On the right side, you got that parabola. Things change drastically from the left to the right. So now I can come to this picture, and I can ask questions. So for example, I might say find limit as x approaches 0 from the left of this function. You don't have a formula. You got the picture. So you have to interpret with the picture. As x approaches 0 from the left, that means I'm in this negative space here. This is what the function looks like. And so what does the output approach as the input approaches this axis right here? And what do you think the answer is? What is the output approaching as I ride along that line? 1. You can trace along the graph. Trace along the graph on the left side. What height does your finger approach? I can't get there, but this isn't about getting there. It's about getting near there. And then I could say, all right, well, what is the limit as x approaches 0 from the right side? What would that be? 0. I think I heard it. Does everybody see? If I ride along the right side, I approach 0. So this is a problem for the general limit, because as I approach from the left, I end up here, but as I approach from the right, I end up here. So I can't make a general statement about just approaching, because it depends on the direction. So we're going to have this rule that if the left-hand limit is not equal to the right-hand limit, the limit doesn't exist. The normal limit doesn't exist. The standard two-sided limit does not exist. And so just think in your mind, if I'm tracing on the graph toward the place where I'm finding the limit and my fingers don't meet, the limit doesn't exist. If they do meet, that's the limit. If the left-hand limit does equal the right-hand limit, then you found the limit. Exclamation point, because that's nice. So let me ask you some questions on this picture. On that picture, what is the limit as x approaches 1 from the left, limit as x approaches 1 from the right, and then the limit as x approaches 1 in general? And I kind of think you're about right. You could probably knock out most of that web work that is open now with just what we've learned today or talked about today. You might be old news to you. I don't know. Is it old news to you, Addie? Yeah. Cool. Nice. Or I don't know if that's cool or not. It's what it is. What'd you get here, Addie? 1? What'd you get here, Addie? I'm not afraid to ask. Left hand. as I ride along the curve toward x equals 1. So this is what x approaches 1 from the left. This is x approaches 1 from the right. And you ride the curves and you look to see, do your fingers meet? And if they do meet, then we're good to go. I want to tweak this example just the tiniest bit. That's not going to change any of the answers. I'm going to actually change the value of x right here at 1. So everything else is going to stay the same. I'm going to put a circle there. But when x equals 1, I'm going to let the output be 2. So we just you can write this down or not, but I just mostly want us to think about it. So now that's what that graph looks like, because right at that one point it jumps up. It doesn't change the answer. This is the point, that the limit isn't never about what happens at the point. The limit is what happens as I get close to it from both sides, or if I'm told, just one of the sides. So this limit here is still 1. I haven't changed it because the height is 1. But let me note this, that f of 1 is 2. The value of the function at 1 is 2. The value of the limit at 1 is 1. Does this make sense? You feel good? Good, good. Yay. All right. I think that's enough for one day, huh? You agree? Probably. We only got 5 minutes left. I need to talk to a few folks. We made it. We got a full recording.